A senior engineer downloads a 7 billion parameter model for the first time. The download completes at 4 gigabytes. She opens the file directory expecting something recognizable. Python files, configuration, maybe a schema. What she finds is a collection of binary tensor files and a JSON config. Nothing that looks like logic. Nothing that looks like rules. No readable entry point of any kind. She has the model. She does not yet know what she has. This article closes that gap. This is what model weights actually are. Models, Part 7. You downloaded 4 gigabytes of binary files. Here's what's actually in them. Section 1. What a weight is. A language model is a neural network. A neural network is a system of connected nodes organized into layers. Each connection between nodes has a numerical value. That value is a weight. The weights of the model, not a representation of the model, not a compressed version of something more readable underneath. The weights are the thing itself. Every capability the model has, its grammar, its reasoning, its domain knowledge, its ability to follow instructions, is encoded in those numbers. When you run inference, the model uses its weights to transform an input sequence of tokens into a probability distribution over what token should come next. It does this one token at a time until it produces a complete response. The weights determine every step of that process. Change the weights and you change the model. Section 2. What the files actually contain. The binary files in a model downloaded are tensor files. A tensor is a multi-dimensional array of numbers. The weight files store the tensors that make up every layer of the neural network, organized by layer, name, and shape. A 7 billion parameter model has approximately 7 billion individual numerical values distributed across those tensors. In full 16-bit precision, each value takes 2 bytes of storage. 7 billion values at 2 bytes each produce roughly 14 gigabytes. Quantized to a 4-bit precision, that same model fits in approximately 4 gigabytes, which is why the model in the opening scenario was 4 gigabytes rather than 14. The JSON configuration file that accompanies the tensor files tells the inference software how to interpret the tensors, how many layers a network has, how wide each layer is, what activation functions to apply, how many attention heads the model uses, and what the vocabulary size is. Without the configuration, the tensor files are just numbers. With it, they are a complete model definition. You will never read these files directly. You will load them with an inference framework that interprets the configuration and executes the forward pass through the network. Understanding what's in them is not about reading them. It's about knowing what you are working with when you make decisions about quantization, fine-tuning, and model selection. Section 3. Parameters and what they tell you. Parameter count is the first number you encounter when evaluating a model and the most commonly misunderstood one. Parameters and weights are the same thing counted differently. A 7 billion parameter model has 7 billion weights. The terms are interchangeable in practice. Parameter count is reported because it's a convenient single number that gives a rough sense of model capacity, how much the model can represent and reason over. Larger parameter counts generally mean more capability and more memory required to run the model. But parameter count is not the only driver of capability. Architectural improvements, better training data, and more sophisticated alignment techniques have allowed newer, smaller models to outperform older, larger ones on many practical benchmarks. A 7 billion parameter model from 2025 outperforms a 13 billion parameter model from 2023 on most tasks. Parameter count tells you about resource requirements more reliably than it tells you about capability. For this arc, the practical implication is straightforward. A 7 billion parameter model quantized to 4-bit precision runs on the minimum viable hardware defined in Part 3. A 13 billion parameter model at the same precision requires the mid-range tier. Parameter count is your first filter when matching a model to your hardware, not your primary filter when evaluating whether the model is good enough for your use case. Section 4. Base weights versus instruction-tuned weights. The weights you download are almost never raw training output. They are one of two things, and the distinction determines how you can use them. Base model weights are the direct product of pre-training. The model learned to predict text across a massive corpus, and the weights reflected that learning. A base model, given a prompt, will often continue as it is completing a document rather than responding to a request. Ask it a question, and it may produce more questions than it has an answer. Base weights encode broad general capabilities without the behavioral shaping that makes a model useful as an assistant. Instruction-tuned weights are base weights that have been further trained on examples of instructions paired with appropriate responses. This additional training process adjusts the weights to produce helpful, coherent responses to direct requests rather than open-ended text continuation. Models labeled instruct, chat, or IT in their name have been through this process. For this arc, you will use instruction-tuned weights. The base model is the foundation the instruction-tuned version was built on. The instruction-tuned version is the one that behaves like a system that you can direct. One practical note on licensing that connects to part 2. Base weights and instruction-tuned weights from the same model family often carry the same license, but not always. Llama 3 Base and Llama 3 Instruct are both governed by Meta's custom license. Some providers release base weights under more permissive terms than their instruction-tuned variants. Read both licenses before committing to a family model for a production build. Section 5. What the weights cannot tell you. Weights encode what the model learned. They do not encode what the model did not learn, what is learned incorrectly, or where the training data was sparse. A model trained on text that underrepresents a specific domain will produce lower quality output in that domain without any visible signal that it is doing so. The weights contain no flag that says confidence is low here. The model produces output with the same structural confidence regardless of whether the underlying weight supports that output well or poorly. This is the property that makes evaluation and monitoring non-optional. The weights do not self-report their limitations. The monitoring layer, covered in part 18, is what services those limitations in production. The evaluation framework in part 17 is what services them before production. Neither substitutes for understanding that the limitation exists at the weight level before you build anything above it. Section 6. What comes next? The weights are what training produced. The next article covers how training produced them, what the process actually involves, and why understanding it changes how you think about fine-tuning, domain adaptation, and the boundaries of what a model can learn from your data.